This is a simple LED connected to my controller that makes it blink. At face value, you don't need a microcontroller. You can simply connect it to power, add a switch, and when it closes, current flows, LED turns on. These, on the other hand, are addressable LEDs. They're also hooked up to my controller, but unlike a simple LED, I can control hundreds of these through a single data wire. However, you can't simply hook them up to power. You need to write software for them. And that's perfectly fine. But I'm curious, what does it take to not use a microcontroller and still control these lights using counters, timers, and transistors? This mess took a while to get working, and this was the first time I saw the colors. Once I cleaned it up, I had this. Taking full use of these LEDs is not fun without a microcontroller. Therefore, V1 keeps it simple. It can select colors and mix them up to 64 LEDs. Let me do a small WS2812 101. First, I want to introduce how color works on these LEDs. All visible light can be split into 3 channels, red, green, and blue. By mixing these values, we can create virtually any color. As I drag the slider from 0 to 255, it goes from off to bright. But why 255? Because each channel gets 8 bits, and the maximum number you can write with 8 bits is 255. All ones is full brightness, and all zeros is off. If we look into the WS812 datasheet, we'll find this color position array. Let me break this down simply. Take one addressable LED. It has 3 channels, green, red, and blue, each one controlled by 8 bits. If I set all 8 green bits to 1 and red and blue to 0, the LED turns green. If I also flip the 8 blue bits to 1, the LED turns cyan, green and blue mixing. This method lets us mix any pattern of 1s and 0s across 24 bits. That's over 16 million colors. But what is a 1 and what is a 0? It can mean 0 volts or 3.3 volts. By alternating voltage levels, we can send data, but binary is a diverse world. It can be light or dark, day or night, true or false. And in the case of WS2812, the binary is time, longer pulse or shorter pulse. The datasheet defines it. To send the 1, the signal is high for 700 nanoseconds, then low for 600. To send a 0, it's high for 350 nanoseconds and low for 800 nanoseconds. So to send data, I just send a long pulse, short pulse, long pulse, short pulse. That's my 1s and 0s. But what does sending data actually look like? Let's say I have 3 addressable LEDs. Each one needs 24 bits of color. So I need to line up all the data on the left. And let's say for LED 1, 2, and 3, I want it to light up red, green, and blue respectively. Through a single wire, I send everything to LED 1. LED 1 takes the first 24 bits for itself, chops it, and passes the rest of the bit data to LED 2. LED 2 does the same. It takes 24 bits and passes the rest to LED 3. Then, as per the protocol, we wait 50 microseconds, the colors latch, and they display. So now we know how many bits, what are bits, and how to send bits. We can start building it on a breadboard. First thing I need to make is a clock, around 800 kilohertz. Naturally, I tried the 555 first. I tried the classic circuits, modified circuits, bipolar, CMOS, but no matter what I did, parasitic capacitance kept me stuck under 400 kilohertz. After some digging, I ditched the 555 and found a simpler way, a Schmidt trigger oscillator. Add a capacitor on the input, a feedback resistor, and the output becomes a square wave. I used a 74HC14, hooked up the parts, and got around 720 kHz. What is nice is that this clock already works from my logic 1 pulses. Highs are around 650 and lows are around 740 nanoseconds. So now I have a clock which also works as my logic 1 pulse train. Now I need another pulse train, and this one will be used for logic 0. I take my main clock and modify it. First, I buffer it through an inverter and then through another inverter. Then I add an RC delay circuit. The idea here is to increase the time the logic stays high, which in turn reduces the time it stays low. Then I invert the signal to get a short, high pulse. However, after measuring the inverter signal, it was not what I expected. It looked almost the same as the original clock, just slightly out of phase. I noticed that both signals had their highs overlapping for about 340 nanoseconds, and I decided to AND them together. That way, the AND gate output goes high only during the time that the 340 nanosecond overlap occurs. After building it, this is exactly what I got. High for around 340 nanoseconds and low for about 900. The outcome of all of this is simple. I have my main clock and pulse trains for logic 1 as well as for logic 0. Next phase is to generate signaling pulses that go high whenever a particular color is selected. We need to know when it's time for green, red, and blue, and they all need to be 8 clock cycles long, therefore we need to count to 24. A binary counter is the guy for the job. It is a simple IC made of flip-flops, and on every clock cycle, it advances by 1 in binary. This particular counter will count all the way to 255. Therefore, when we reach 24, both 8 and 16 are high. We can AND them together and reset the counter back to 0. If you notice, while counting from 8 to 15, position 8 is always high. That is 8 clock cycles, and we can track position 8 to know if it's time for red. Same goes for counting from 16 to 23. That is also 8 cycles. Position 16 is high during this period, while 8 is low. By tracking 16, we know when it's time for blue. We cannot really use this trick for green. However, green happens when counting from 0 to 7, when red and blue are not happening. In other words, the green signal is when position 8 and position 16 are low. We take these signals, invert them, and AND them together. Now, whenever this AND gate output is high, we know when it's time for green. Here's the schematic so far. We now have 2 clock signals. Clock 1, clock 0. One has longer pulses, the other one has shorter pulses. And we just added a circuit for 3 identification signals. If we measure our signals on a breadboard, you can see how they go high, 1 at a time for each color. Even more importantly, they're 8 clock cycles long. I think of the identification signals as envelopes. If we insert a pulse train for logic 0 into these envelopes, the LEDs will turn off. But let us say we change the red envelope to a pulse train with longer high period. That indicates all ones and turns the red LED fully on. So how do we control this on demand? In this simple case, I went with a button. Whenever the button is pressed, it goes high. And once the identification signal goes high, it activates that color. I built 3 of these blocks, 1 for each color. To allow for color mixing, we OR all 3 of them together. To turn these envelopes into usable signals, we pass the result through another AND gate. Here is an example. Let us say I press the button for green. It travels through the AND gate into the OR gate and activates the AND gate for clock 1. The time the envelope signal is high is the time and position when the AND gate outputs longer pulses, essentially enveloping the signal. Here's how it looks after building and measuring. As you can see, the signal is output only when the identification is high. But that's not it. In my case, I want LEDs to be off all the time, except for when a button is pressed. To do that, we OR the 2 signals, short pulses and long pulses. Because the long pulses are disabled when no button is pressed, the output is always short pulses. It is only when I press a button that the short pulses turn into longer ones at the exact time and position. If we look back at the datasheet, there is one important requirement, the reset I mentioned earlier. Let us take an LED strip and our generated bit stream. In the end, I chose an AND gate. I can pass my signal to one input, and by writing the other one high, it will pass the data to the LED strip. If I write this pin low, then the LED strip data will go 0. I just need to find this magical input that will automate this toggling for me. If you recall the original binary counter, I basically added another one. I took the reset from the first counter and used it as a clock to drive the second counter. I wired the position 64 output to an inverter and into my AND gate. This way, the AND gate always passes the LED unless the counter hits 64. Then the LED line goes low until the counter is back to 1. After building it, I managed to generate my gaps. And now finally, let me introduce the full picture. So first, we generate a clock around 800 kHz, which we also use for logic 1. Then we turn this clock into shorter pulses for logic 0. Next, we build color identification signals for green, red, and blue, each 8 clock cycles long. Using AND gates, we combine them with buttons to allow on-demand selection. We turn those identification signal envelopes into logic 1 pulses. Then we build logic to decide whether a long pulse or a short pulse should be sent. Last but not least, we generate a reset signal and combine everything in the final stage to create an addressable LED data stream. Here's the first test after building it on a 5x5 LED matrix. When nothing is pressed, the lights are off. Using the buttons, I can switch on green, red, blue, or mix red and blue to get purple. Before the final test, I wanted to turn this into a soldering kit. I wanted it to be 55 by 55 and symmetrical along the purple line. After laying out the PCB and routing everything, ended up with this, including a through-hole addressable LED, so you guys can solder it as well. I exported it and waited. Anyways, here's the PCB. After soldering all the parts and spending an entire day debugging, I finally got to the end. A self-sustained addressable LED driver without a microcontroller. 3 buttons, red, blue, and green. Hold 2 at a time and they mix for purple, cyan, or white. 24 bits generated by an oscillator, a counter, and some logic gate. It also has an onboard LED, so you don't need an LED strip.